Hello, we're going to do another practice problem. Today we're going to do 11.72 out of the textbook. Here it says two beams support a uniformly distributed load as shown in the figure. And beam 1 is supported at the fixed support and then supported by the simply supported beam. So beam 1 is the cantilever beam here, the steel beam, and then beam 2 is the simply supported timber beam. And a couple of notes here. It says, in the unloaded condition, beam 1 touches but exerts no force on beam 2. And then we're given a bunch of information about the properties of each beam. And it says here, determine the maximum flexural stress in beam 1, in the timber beam, so beam 2, and then in the steel beam, which is beam 1, if the timber beam was removed. So there's a lot of information here that's given. So what I want to do first is actually just identify all this given information. So the first thing I'm going to do is let's write, steel beam, and then just all the given information that we have here. So the beam 1 has a depth of 400 millimeters, right? So we can say depth equals 400 millimeters. Okay, and that 400 millimeters, what's important about that is if we have an I-beam, right, which is the steel beam, that 400 millimeters is the entire distance, right? So the neutral axis then is 200 millimeters. So the neutral axis is 200 millimeters. Okay. And then we have a moment of inertia, which is given, which is nice of them to do that for us. And we have a moment of inertia of 1 equals 130 times 10 to the 6 millimeters to the 4th. We have an overall length of member 1 is 3.5 meters. Elastic modulus of 1 is going to be 200 gigapascals. Okay. And then just for fun, since we know we're probably going to have to do it anyways, let's multiply E and I together already. So if I multiply E and I together, and be careful, unit conversions, right? So we have units that we have to account for. You should get 26,000 kilonewtons meters squared, okay? And then our distributive load that's acting, or W, that's acting along member 1 from A to B is going to be 30 kilonewtons per meter, okay? So that's all the given information that we can take from this paragraph of the steel beam, so member 1. And then we'll do timber beam. And here, the first thing I think is L sub 2 is 5 meters, okay? And then L sub 2 divided by 2 then equals 2.5 meters, right? And then the moment of inertia, which is not given, but we can find that because the section property here actually states that the timber beam is 175 millimeters wide and 300 millimeters deep, right? So with our shape, we have BH cubed over 12 is going to equal 175 millimeters multiplied to 300 millimeters cubed divided by 12. And so I sub 2, our moment of inertia for the timber beam, is going to equal 393.75 millimeters to the 4th. Okay. We're given our modulus of elasticity, so E sub 2 equals 12 times 10 cubed megapascals, right? So converting to megapascals, I know they gave us 12 gigapascals, but I did megapascals to help do the conversion because I kind of quickly went over it in the last one, so I'll just kind of break it down again. If you do this unit conversion here and then E to I2, it's a little bit easier to do this multiplication here. And so you should get, if you multiply these two together, moment of inertia and modulus of elasticity, you should get 4,725 kilonewtons meter squared, okay? All right, so that's all the given information basically, right? So we've identified all that. So what do we do first? Well, we're asking for the maximum flexural stress in each of the beams and if the timber beam was removed, okay? So what we're gonna do, or what I'll do first, is take the cantilever beam, an analysis of the cantilever beam first, which is member 1, okay? And the cantilever beam, if you look in the appendix, right, or the class handout, we have formulas to be able to determine what the deflection will be at a given point, right? So the cantilever beam, if we look at it and say this is my, if I zoom in, what is the cantilever beam, right? Here's our distributive load, right? And here's the side, but there's at the very end, that timber beam at the end, but the timber beam is going to be exerting a force, right, on the cantilever beam, so the force is actually going up like that, okay? So this is our loading condition that we have on the cantilever beam. So in our formulas that we can use, what we'll do is use the superposition method, and we're going to break this up into 2 separate beams, right? So we'll have the distributive load, right, cantilevers, and then we'll do the point load, right? So the point load, and each one of these has a formula for it, right? And this is the cantilever, okay? And so for the distributive load, we can look on the formula sheet, and it's, and I'm sorry, I'm using delta because at point delta is the point that it's deflecting, right? So the deflection then equals negative WL to the 4th, and we're going to do member 1, so sub 1, and then 8 E sub 1, I sub 1. And then deflection for the point load at delta is then going to equal a negative PL sub 1 cubed divided by 3 E sub 1, I sub 1. So we need to note on the point load, we need to note that P equals the reaction that's occurring at this point delta, right? And what's delta? We could just call it, if we were to draw a free body diagram of the timber beam, that would be P is going to be negative the force in the y direction at D, okay? So going back to our simply supported beam, actually, so we're pretty much done with this. Let me leave it in units right now for this. But let's look at our simply supported beam, okay? Simply supported beam is, it has one loading that's acting on it right in the center, right? And that one loading at the center, okay, there's a formula for this as well, so we can look up at our table again, and we can find the deflection at point D, and what that deflection is going to be negative, and then again dy L sub 2 cubed over 48 E sub 2 I sub 2, okay? So the sum of these deflections, right, is going to equal, or what we can do is equate them together to be able to solve for what the unknown is, because everything in these equations are known. So the distributive load is known, the lengths are known, the modulus of elasticity and moment of inertias are all known, and even I went ahead and multiplied them together up here so that they're already done. The only unknown in here is this reaction between the two members, so d sub y, right? So let's relate these equations together. So we have negative WL sub 1 to the 4th over 8 EI sub 1 plus, oh, and I'm putting a plus because right here, if you plug this in to this guy, this negative here and this negative here cancel, it becomes positive, okay? And this, so plus delta sub y cubed over 3 E sub 1 I sub 1. And then this will equal the same deflection that's occurring in the simply supported beam, which will be negative delta sub y L2 cubed over 48 e sub 2 I sub 2. So what we can do then is move this over here and move this over here, and then factor out the delta sub y. So you end up with delta sub y equals L sub 1 cubed over 3 e sub I1 I sub I1 plus L sub 2 cubed over 48 e sub 2 I sub 2, and then all of this equals W L sub 1 to the 4th, and then 8 e sub 1 I sub 1. Okay, so then what you could do is just take this portion here and divide it to this side, so it'll be d sub y equals a whole bunch of stuff, but everything else, once you do that, everything else will be known, right? And so what we can do is all the properties that we already identified up here at the very beginning, all these properties up here, we've already found them, so you can just basically plug and chug at that point. And once you do, I'm not going to do that work right now, but leave it to you. Once you do, you should get d sub y to equal 19.6613 kilonewtons. Okay? So now that we know d sub y, this is important, because now how do we determine the flexural bending stress, right? And this is, this is needed information to solve for the rest of it. And the purpose of that is to be able to calculate what would our moments be, because to find our flexure stress, in this diagram, let me zoom in on the diagram here. So let's analyze the cantilever beam, right? And we need to determine the maximum moment on this beam, right? And so we know that it's cantilever, so there's a moment here that we have to find, right? And the moment at A, and then we need to find a moment in the timber as well. So in the timber, what we could do is maybe pick one of these ends, right? So maybe point E, and then we'll have to sum the moments at point E equaling 0, so to be able to calculate what the moment is along this member. Okay, there's several different methods that you could use to be able to solve for this. We've gone over it in other chapters and statics and other sections, but what I'll do is just sum the moments at A, right, for the first one to be able to find the flexural bending stress of the cantilever beam. Sum the moments at A, right, and so part A. Sum the moments at A equals 0, and then that'll be MA, MA, and then minus, we'll leave it all in variable form for now, L sub 1, and then L sub 1 over 2, plus D sub y, which we've already found, multiplied to L sub 1, and all that equals 0, okay? And then M sub A, the moment at A equals our 30 kilonewtons per meter multiplied to the distance, which is 3.5 meters. And then that's acting halfway along the member, so that's going to be over 2. And then minus d sub y, which was 19.6613 kilonewtons. And the length is 3.5 meters. Okay, so the maximum moment is going to be at the fixed support, and that's going to be 114.936 kilonewton meters. Okay, that's our maximum moment. But let's go ahead and do a unit conversion and turn this into Newton millimeters, right? So M sub A is then going to equal 114.936 times 10 to the 6th Newton millimeters. Okay, so then for our maximum bending stress, right, of member 1 is then going to equal my over I. Okay, but what's y? Well, y, right, remember what I was drawing up here at the very beginning, and I said the steel beam we were given a depth of 400 millimeters. Well, from the neutral axis, right, to this edge is 200 millimeters, and we want to use this outermost edge because that's where the maximum bending stress is going to be. Okay. So going back down, when we plug all of our values in here, we can get 114.936 times 10 to the 6 Newton millimeters multiplied to half of that, because it's going to be, remember, the 200, half of the distance, 200 millimeters. And then divided by the moment of inertia, which in the steel beam, that was given information. 130 times 10 to the 6 millimeters to the 4th. So 130 times 10 to the 6 millimeters to the 4th. Okay? So max bending stress for the steel beam, run through this calculations. All the units should be able to calculate or cancel, and not all of them, but they're compatible. Let's say that. Okay. And so max bending stress is then going to be 176.824 megapascals, unit of pressure, remember? And that is the answer for part A. Okay. So part B. So now we want to find the maximum flexural stress in the timber beam. Okay. So the timber beam, I'll go over here to this side. What we'll do is sum the moments like I was talking about before. So the timber beam is this simply supported beam. This is C and this is E, right? So let's sum the moments about E, and sum moments about E equals 0. Okay, and so that would be, we have C sub y multiplied to L sub 2 plus D sub y multiplied to L sub 2 over 2, right? And this equals 0. There's nothing else there. So C sub y, we need to find C sub y, I guess. So C sub y then equals, dividing out the L's would go away, so it would just be C sub y equals D sub y over 2. Interesting. Okay. So makes sense because it's only one loading directly in the center, so we can just divide 19.6613 by 2. We get 9.8307, and that's kilonewtons, and it's acting up. Okay, so now with this information, what we can do is determine again from the formulas, the same place where we got the deflection formula. So in the handout or in the appendix at the back of the book, we can look it up and find that our moment maximum is going to be our reaction force, C sub y, multiplied to half of our length. Okay, and so m sub max then equals 9.8307 kilonewtons multiplied to our distance, which is 5 meters, divided by 2. So this will be kilonewtons and meters. We'll end up with 24.577 kilonewton meters. And again, changing it back to millimeters and newtons, so we can just plug it right into our flexural bending stress formula. We'll just say it's multiplied times 10 to the 6th, and now it's newtons, millimeters. Okay? So our maximum bending stress for the timber beam, so max bending stress of timber beam, so beam 2, is going to equal our max moment, y, over I. So what's our y distance, right? So let's go back to our given information that we wrote here. So I said that the height, right, was 300 millimeters, right, for when we were calculating our moment of inertia. So half of that, 150 millimeters, is going to be the y value, because again, going back to stress, if I was going to draw our profile view here, and this was our neutral axis, okay, our bending stress then is going to be maximum at the ends. So this is max, and this is equal to 0, okay? So we can do our bending stress of beam 2 is then going to equal our moment. So 24.577 times 10 to the 6th Newton millimeters multiplied to 150 millimeters divided by the moment of inertia, which we calculated earlier to be 393.75 times 10 to the 6th millimeters to the 4th. So for the timber beam, max bending stress is then going to equal, rounding up a little bit, and so 9.36 megapascals. Okay, and this is the answer for part B. Okay, so now part C asks, what if the timber beam was no longer there, right? So let me zoom in on our diagram here. So now the timber beam no longer exists. And what are we left with? If the timber beam no longer exists, then we just have a cantilever beam, right? All we have is this scenario here. So if you look in the appendix, right, or your handout, you can find, we've already found the maximum moment. We determined that's going to be the support. We know what our deflection is. So now we can actually find what the bending stress is going to be, okay? So our maximum moment, I apologize, our maximum moment that we found earlier was with the support in there. So the same place where the appendix is, where we got this information, we can find what the maximum moment is. Okay, so our max moment, right, with that appendix is going to be, let's say it's the distributed load, the length squared over 2, okay? And our distributed load was 30 kilonewtons, so kilonewton per meter. And then our length was 3.5 meters, and we'll square that divided by 2, okay? And then this will equal 183.750 kilonewton meters, okay? And so now the bending stress in the steel beam without the assist from the timber beam is going to be this moment, which is 183.750 kilonewton meters multiplied to our 200, so the half of the depth of the steel beam, so this is millimeters. Now we have a unit conversion issue, so and then divide by the moment of inertia, which is a given, times 10 to the 6 millimeters to the 4th. And so then this would be, we'll multiply this to 1,000 millimeters per 1 meter, and then you should get, divide all this out, and you should get 282.692 megapascals. And then this is the solution for part C.